We continue our discussion on piezoelectric actuators. And the last time we stopped here, I was going to explain this behavior here, where we have a very strong nonlinearity but no hysteresis, and obviously those actuators have some merits. Those which also, that's the same actuator here, which is, I'm sorry, I only now see that the legend is disappearing, but that's this actuator here, which also has the lowest creep, and the one with the biggest hysteresis would, I think, also have a, so these other ones would be here, and the hysteresis and the creep are commensurate. What kind of actuator we have here without hysteresis? The hysteretic ones we have already discussed. We have related this to domain wall motion. So does it mean that we don't have a domain wall motion here? Well, actually, these are actuators that are not ferroelectric. They are relaxer materials, which at room temperature are not ferroelectric. They use electrostrictive effect. So that would be also, I don't know, I think this reference here is from former ferroperm in Denmark, and M here is proportional to permittivity and Q. So to get a large electrostrictive constant, you need large materials with large permittivity, and that's what relaxer ferroelectrics give you. Now, they don't have ferroelectric domains to give you hysteresis, but they do have internal nano-size objects, which are called polar nanoregions. Those also move under external field, but the hysteresis is much, much smaller than in ferroelectric materials. So you can get almost non-hysteretic and almost creep-free behavior. So this is interesting if you need extremely low hysteresis, extremely high precision behavior strain. And I will give you some examples where this was used later. Other materials that would give you low hysteresis are relaxer ferroelectric solid solutions. So here it would be PMN, lead magnesium niobate, and ferroelectric materials which could also give you hysteresis-free behavior are also contain this lead magnesium niobate or lead zinc niobate in solid solution with ferroelectric material. And these are ferroelectric, and they have ferroelectric domains. So why do they give this low hysteresis? Absence of hysteresis, unhysteretic response, or very low hysteresis. Well, again, this is what we discussed previously with anisotropy of the piezoelectric effect and the morphotropic phase boundary. So you would have this situation in which you have a rhomboedral material where polarization is along 1, 1, 1 pseudo-cubic directions, and you actually use, you apply field like this along the 0, 0, 1 pseudo-cubic direction. So away from polarization. Now, if this angle here is approximately 54 degrees, something like that, you would have that all domain states that you can have here. If we look at the cube and you polarize this crystal, then you would have domains polarizations and domains like that. They are all equivalent with respect to, well, this is under an angle. I'm not drawing it very nicely. And your field is here. So projections of these polarization vectors to polarization are all exactly the same, which means that they are energetically equivalent with respect to the applied field, and there is no reason for them to move under the field. This is so-called for R state, for rhomboidal states, and you can have two orthorhombic or one R or similar in tetragonal states. You can read this paper by Vada and Schraut that I recommended you before from end of 1990s or beginning of 2000. So only under those conditions these materials will not give you hysteresis. And they give you also very, very large response, because this D33 coefficient here uses this polarization rotation at morphotropic phase boundary compositions. It is a function of D15, D33, D31, and so on. I think D32 coefficients in a rhomboidal phase, and it is D15, which is, because of polarization rotation, particularly large, which will give you large D33 in this direction. D33 is very small along polar direction, but becomes large when you apply field of polar direction. And this is called, I will repeat again, domain. Engineering. Read papers by Vada and Schraut. There is one paper together, end of 90s, beginning of 2000, and then several papers by Vada alone for a barium titanate, for a PMN, PT, and other materials. So you can get very large strain, unhysteretic, very little drift, excellent for actuator applications. Of course, these are single crystals, so they tend to be expensive. You can also use ceramics for this. They will also have reduced hysteresis. There are many actuator applications. I cannot possibly go through all examples. To see different types of actuators, please consult this book by Kenji Uchino, Piezoelectric Actuators and Motors. But basically, you can use them in for light deflection, laser light deflection, in optics. There you would use flexural actuators. For XY positioners, for fuel injection control. In fuel injection control in diesel cars and also with the gasoline fuel, you want to inject fuel only at a moment when to get optimal volume fractions or pressures of air and gasoline. Partial pressures of different gases in the engine, and that ensures that you have optimal burning of toxic gases or decomposition of toxic gases. And this helped a lot to reduce toxicity of diesel engines. Now with the advent of electrical cars, actuators can be used in cars for other things. But this was produced in Japan, in Europe, for example, by Bosch in tens of millions of pieces, these piezoelectric actuators. And they are made of multi-layer, made by tape-casted, I think, elements. Now, one application of these relaxer actuators, electrorestrictive, which are not hysteretic and which have a little drift is in optical applications. And here is the one that was used in Hubble telescope. As you know, at the end of 80s when Hubble was, in the 80s when Hubble was launched, there was an error in its mirror and it gave not so good pictures. So in one of the missions of Space Shuttle, the astronauts were able to put on the bottom of this telescope mirror electrorestrictive actuators, and by applying electric field it was possible to deform this mirror and compensate for this error in polishing the mirror. And then the pictures were much more detailed with more information obtained. And here you see also some pictures. This was before the adjustment, and this is after the adjustment with piezoelectric actuators. Also here before and after, and you see how many more details you can see just by this simple deformation of the mirror with electrorestrictive actuators. And they can operate very well in this vacuum in space and low temperatures. You can get similar enhancement of the picture by software, but of course we prefer to do it with the hardware. And now I would like to discuss a little bit the scanning systems with piezoelectric materials. This is used in atomic force microscopes, but also in other places where you need scanning and control of scanning with a sub-nanometer resolution or even better. So how does it work? You have a piezoelectric scanner here. You put your sample on the top of that, and that sample has some surface profile that you, for example, want to examine. The cantilever doesn't move. It's the PZT scanner that moves in the plane. And the tip is either measuring the current or touching the surface. You have a laser which shines on the tip and reflects from it. And if the surface is uneven, then this angle here would move in that plane and also in a perpendicular plane. And you can map with a nanometer resolution. Let's say the tip itself has some curvature, but you can achieve certainly nanometer resolution here, and this can be done with piezoelectric elements. So the tubes that are used are like the ones that I showed you in introduction. This one is by Physic Instrumente. So the question is, which piezoelectric coefficient is used here? You apply this central electrode here is connected to ground, and then you have 4 electrodes. Okay, it's segmented into 4 equal pieces, and they are separated by the electrodes are not continuous. And so which effect we are using? Remember that what we want is the motion in this direction and in this direction, and we would really like to achieve the circular motion, so have control in this whole plane. So which effect is used here? Well, if I'm applying negative field, negative voltage between this and the ground on this electrode, it would, for example, tend to shrink, but the rest of the sample wouldn't. And that means that this tube would bend if it is clamped here on the bottom. If you apply now voltage, positive voltage here, it would bend even more. And by applying different combination and the strength of these voltages, positive and negative, on different electrodes, I can achieve almost any kind of movement in the plane. And X motion or Y motion is given by this relationship here. So it depends a lot on L, length of the tube, L square. So the longer is the tube, the more motion you can get. The interesting thing here is that these tubes are actually rather inexpensive to make. You can get it by extrusion or even by machining. However, when you buy it for your AFM or a piezo force microscope, the price is in the thousands of, the scanner is in the thousands of euros or dollars or francs. They get very expensive. So that's one of the big successes of these piezoelectric actuators, and there are many, many others. The market of piezoelectric actuators nowadays is several billions of dollars per year, and they are used anywhere in precision mechanics, life sciences, semiconductors, microelectronics, optics, in data storage, and so on. Of course, some of these things change. We are recording data now differently than we did 10 years ago, but there are new applications coming out. For example, the Mars rover, when it drills the hole in the Mars to take samples, it actually uses a piezoelectric actuator, and they test them in Jet Propulsion Lab in Pasadena in California. They use very powerful piezoelectric actuators for that. You cannot afford on such, in that atmosphere on Mars, to have other types. Either they are too heavy or cannot stand the temperature or dust and so on. So these are excellent. Those actuators are tested on in deserts in California or on Antarctic, where temperatures are very low. Many applications in the military and civilian applications and so on, even for games. There is a pachinko game in Japan where you force a ball to jump from one place to another, and it's very popular, and that was one of the first applications of piezoelectric actuators. So there are many of them. I would now like to finish this section by discussing very briefly piezoelectric motors. There are thousands of types of piezoelectric motors with thousands of patents on them, most of that in Japan, many in United States. And interestingly, some of the first piezoelectric motors were made in Europe, in Lithuania at Kaunas University of Technology. In 70s, they were developing these piezoelectric sensors and actuators and motors for space program, for military applications, and many of those early patents that were developed in 70s in Lithuania found their way after breakup of Soviet Union in 90s to the West. Please, if you're interested in piezoelectric motors, consult the book by Kenji Uchino, Piezoelectric Actuators and Motors. There are many ways in which you can make the motor. What is the difference between piezoelectric actuator and motor? Well, every piezoelectric motor is actually piezoelectric actuator, except that in a motor you have a continuous, let's say, periodic motion or something like that. So one way to do it, the key is to make some asymmetry in your system, and the one way to construct a piezoelectric motor is to take a piezoelectric disc and segment it into different electrodes, which would be periodically poled, so plus, minus, plus, minus, plus, minus. And then you put metal legs here, and then if you drive this one so that part extends and this one shrink, that leg would bend, okay? And so your piezoelectric material and whatever is on the top of it glued would make this motion, and then whatever is on the top will be and supported by these legs will rotate on there would be a standing wave, and it would rotate, and you can change the direction of this rotation. So the motor itself doesn't only transmits a wave, a standing wave in the structure, and it's the object that you want to move which is rotating. Of course, there is a friction problem here, and that's a problem with many of piezoelectric motors, but they work very well. The piezoelectric motors are used in many places. You are using them. For example, in many full-sized cameras, you are using piezoelectric motor, full-size piezoelectric motor for focusing, for moving the lens. You are also using piezoelectric motors of different type, linear type, in telephones for focusing. If you have expensive cars such as Lexus, they are using piezoelectric motors to open and close windows. These motors are noiseless, they don't have rotating parts, and there is no wear and tear, and except for this friction problem. So they really work very well, and usually have a less power consumption than electromagnetic motors. You can make linear motors by the same principle as I just showed you for rotating. You have one positive, one negative, negatively polarized piezo ceramic glued on a piece of metal and then placed in a rail. And if you drive these two, one will shrink, the other one will expand. The steel will deform in such a way, and these legs will move in such a way to make this whole thing moving in a linear way, up and down in this picture. And you can use this to deliver light pieces, paper for stores in windows, in industry, to transport small objects and so on. Other type of piezoelectric motors look like this. Again, you have a piezoelectric ring, which is asymmetrical, with segmented electrodes poled plus and minus. And when you put a piece of a metal on the top of it, fix a piece of a metal on the top of it, you will induce a surface acoustic wave in that metal. So the particles would move in this direction, and the wave would go like that, and that would force this slider on the top to rotate around. Again, the only problem is really this friction here. I will talk about surface acoustic waves a little bit later, but basically if you have a proper piezoelectric effect in a properly excited piezoelectric motion, you can excite on the surface of a material, elastic material wave. These waves are similar to earthquake waves. When you have an earthquake, the seismic wave moves only on the surface and can very quickly go around the whole Earth. As I said, there are thousands of piezoelectric motors. I'm just giving you an idea. Eugenio's book is a very good one. You will learn about inchworm motors and many other types. So this concludes this section on actuators. We will now go with other applications of piezoelectric materials.